The second part of video 3 in our mole unit is on empirical formulas. You can see there are several learning targets here, 4 different learning targets. We want to define empirical and molecular formula. We want to be able to determine the empirical formula of a compound from its molecular formula, determine the empirical formula of a compound from percent composition data, and finally determine the molecular formula of a compound from its empirical formula in molar mass. So we'll hit up each of these learning targets in this video. You can see there's a very large list of resources here, several different videos, looks like about 4 or 5 videos there. I think they're all good. Okay, they're all on examples, slightly different variations of finding empirical formulas and molecular formulas. I would definitely check them out, and then listed some good practice there as well. Alright, so first of all, just some definitions. As you can see, I already have them typed in here for you. Let me zoom in here a little bit and see them a little easier. When we talk about the molecular formula for a compound, you can see the definition. It's the formula indicating the actual number of atoms of each element in a molecule of a compound. So for example, the formula for water, and it is the molecular formula for water, is H2O. Okay, this means that if we were to look at a molecule of water, there would actually be 2 hydrogen atoms and 1 oxygen atom. Okay, likewise, if we had, let's say we had sucrose, which is C6H12O11, C6H12O6. In a molecule of sucrose, that's a type of sugar, there would be 6 atoms of carbon, 12 of hydrogen, 6 of oxygen. Okay, that would be what would actually make up that compound. The empirical formula it's also a formula, but it only indicates the simplest whole number ratio of atoms of each element in a compound. So for water, that empirical formula is still H2O, because it can't get any simpler than 2 to 1. There's 2 hydrogen atoms for every 1 oxygen atom. I can't divide those by any other number to make them smaller and have them still be whole numbers. Unlike for sucrose, I can divide all those numbers by 6. 6 divided by 6 is 1, so that's C. 12 divided by 6 is 2. 6 divided by 6 is 1. So the empirical formula for the C6H12O6 is CH2O. Again, it is just the simplest whole number ratio of the elements in the compound. So if you jump down here and look at the example problems, we'll get to those other steps here in a little bit. It just simply asks us to determine the empirical formula for each compound. One of the videos up there, I'm not exactly sure, it's either the second or the third or fourth one up there, gives you a whole bunch of examples of these. I definitely check that out. So here in the examples, we're given the molecular formula H2O2, and we're asked to find the empirical formula. Well, ask yourself, what number, has to be a whole number, can I divide both of these subscripts by and still have whole numbers? Well, the answer there would be 2. I can divide 2 by 2, and that would give me 1. So the molecular formula for H2O2, which is hydrogen peroxide, by the way, is HO. So ask yourself, what number can I divide 8 and 18 by? Well, if you said 2, that is correct. If I divide them both by 2, that would give me C4H9. Now, I can't make it any smaller than that because there's no number that I can divide both 4 and 9 by and still have whole numbers. Okay, so that's the simplest whole number ratio I can get out of that. What about in 205? Are there any numbers that you can divide both 2 and 5 by and still make it smaller and have them be whole numbers? The answer is no. So here the empirical formula is also the molecular formula. It's in 205. Okay, and then if you look at the last one here, what number can I divide all those subscripts by? Well, they're all even numbers, so I know I can divide them by 2, and that is the largest number I can divide them by. So if I divide them all by 2, that gives me C5H6O. And I've divided them all by 2, and I have my empirical formula. And I've just realized here, it just so happens in all these examples, we've divided by 2. Let me give you another example where we could divide by something else. Say we had, let's see, this, I don't know, yeah, this compound exists. Say we had C4H12. Okay, let's say that was the molecular formula. Well, I could divide them by 2. That would be correct as far as getting a number I could divide them by. That would give me 2 and 6. But I could divide it by even a larger number. 4 and 12 are both divisible by the number 4. So if I divide them both by 4, that would give me CH3. That would be my formula there. Alright, so this is how we can find an empirical formula from a molecular formula. Alright, the next set of problems deals with these steps here. And I've already written them in here, so you don't have to take the time to write them down. What I'm going to do is I'm just going to go ahead and flip to the next page. And then you'll want to keep this first page handy. I know that probably means you'll be flipping back and forth a little bit. But I'll be coming back to these steps here that we'll take a look at and see how we are able to determine an empirical formula. Alright, if we look at the next problem here, we are told eugenol, that's how you pronounce that, eugenol, is a main component of olive oil. Eugenol is 73.14% carbon, 7.37% hydrogen, and the rest is oxygen. We are told the molar mass of eugenol is 164.2 grams per mole, and we are asked to determine the empirical and molecular formulas of eugenol. So this is the opposite thing that we learned from the last video. In the previous video, we were given the formulas and we were asked to calculate these percent compositions. Now it's the opposite. We're given the mass percentages or the percent compositions, and we have to find the formulas. So if you look at the steps here, if you look at the steps to determine a molecular formula, or excuse me, an empirical formula, that's what we're going to do first. Our first step is to convert the masses or percents to moles. So if I go and look at the problem here, I am told that 73.14% of this compound is carbon. Now that's not actually a mass. However, if I think about what percent means per 100, if I just pretend I have 100 grams of the compound, then that means I'm going to have 73.14 grams of carbon. Okay, if we just say we have 100 grams, then it makes it really easy because now these percentages just turn into masses. So I need to convert this to moles. That's the first step. So this is just a basic grams to mole conversion. So you're going to use the molar mass. So the molar mass of carbon is 12.01 grams per mole. Okay, I'll just do this for each of these. So I'll leave that blank. I'll come back and put in an answer in a second. For hydrogen, I have 7.37%. So just turn that into a mass. 7.37 grams of hydrogen. And use the molar mass of hydrogen to convert to moles. And then we're told the rest is oxygen. Well, I know they have to add up to 100%. So if I just subtract these other two from 100, 100 minus 73.14 minus 7.37, that will show me that there's 19.49% oxygen. So that will be the mass of oxygen I want to use. So 19.49 grams of oxygen, and again use the molar mass of oxygen to convert it to moles. Alright, so just do these calculations here real quick. For carbon, that would give us 6.090 to 4 sig figs. 6.090 moles of carbon. Okay, for hydrogen, 7.37 divided by 1.01, that gives us 7.30. It's only 3 sig figs there. And then for oxygen, 19.49 divided by 16, and I get 1.218. Alright, there's the first step. So let's take a look at the second step. The second step tells us to find the mole ratios by dividing by the smallest number of moles. Okay, so if I go back to my problem here, I'm just going to set up a ratio. I know that in this problem, in this compound, there will be 6.090 moles of carbon for every 7.30 moles of hydrogen for every 1.218 moles of oxygen. Now, I want a mole ratio, and I want it to be the simplest ratio I can make it, and it needs to be whole numbers. So the process we're going to do here is we're just going to divide all of these by the fewest number of moles, which you can see here is 1.218. So divide them all by 1.218, and then we'll just see what that gives us then. Alright, so we have 6.090 divided by 1.218. Okay, and that is exactly 5 moles of carbon. And I have 7.3 divided by 1.218, and that gives me 5.99343. Now, you might think, well, let's see, I should have 3 sig figs, so that'd be 5.99. Here's the thing, though. These ratios are simple ratios, they're whole number ratios. This is incredibly close to 6. So that's what it is. The only reason why we don't get 6 is due to sig fig rounding from earlier, and maybe any sort of measurement rounding that occurred whenever these percentages were measured. So that's 5 moles of carbon to 6 moles of hydrogen, and then obviously anything divided by itself is 1. So that is 1 mole of oxygen. Okay, so we've done step 2. Step 3. If necessary, multiply ratio to obtain whole numbers. Well, if I look at the ratio that we wrote, these are all whole numbers, so I don't need to do anything there. Our next example, we'll see a case where when we do the division, we won't get all whole numbers, so we will need to do that step. All right, last step is to simply write the formula. So if I go back and look at the ratio, I can see there are 5 moles of carbon for 6 moles of hydrogen for 1 mole of oxygen. So my formula is C5H6O. That is the empirical formula. Okay, so I found the empirical formula. We're also asked to find the molecular formula. Okay, and you can see there's a list of steps to do that. Our first step is to calculate the empirical mass. What that is, it's just the name I give for the molar mass of the empirical formula. Just a little easier to say. So if we just look at the empirical formula that we just found, if I calculate the molar mass of that, so I'll just do that. We have 5 times 12.01 plus 6 times 1.01 plus 16.00. This gives me 82.11 grams per mole is what that molar mass is. Okay, so there's the first step. The second step, we are going to divide the molar mass by the empirical mass. If you look in the problem here, we are given the molar mass for the compound. We're told it's 164.2. So we're going to take that molar mass, and that would be the molar mass of the molecular formula, and we are going to divide by the empirical mass that we just found. Now when you do this, this is going to be a whole number. Okay, so if we plug this in here, 164.2 divided by 82.11. Now you might be thinking, well wait, you just told us this is going to be a whole number. I see 1.99997, etc. here. Well, that's really, really, really close to 2. The only reason why it's not exactly 2 is simply due to rounding and sig figs. So this is equal to 2. The reason why it will always be a whole number, or something really, really, really close to a whole number, is if you think about the definition of what an empirical formula is. In fact, I'll just bring that first sheet back up here. We know that these molecular formulas are some whole number factor larger than these. Okay? To go from molecular to empirical formula, I just divide the number of atoms by some number. Okay? Which means the masses of these two things have to be some multiple of one another. If you do this calculation and you get something like 2.3, okay, then something isn't right here. Okay? Either you calculated a mass wrong or your empirical formula isn't right. Alright, so that being said, we know this ratio here is 2. So what this tells us is there are 2 times the number of atoms in the molecular formula as there are in the empirical formula. So if I look at the steps here, we're told, after we divide the molar mass by the empirical mass, we want to multiply the empirical formula by the ratio of the masses. So the ratio of the masses is 2. So all I'm going to do is I'm going to look at the empirical formula. I'm going to multiply all those atoms by 2. So that gives me C10H12O2. And that is the molecular formula. Alright, the next example is just the same thing. as the first example here, or the number 2 here. I thought you guys probably want to see another example because it's not immediately clear right from the start. Alright, so same thing here. We're given percent composition. We're told the molar, not the molar masses, the percent compositions of the elements. We have carbon and hydrogen, and we're given the molar mass, and we're asked to find the empirical and molecular formulas. So our first step, we're just going to convert those masses, or in this case percent, but we can just call them masses, into moles. So this is just a gram to mole conversion. Alright, so let's just figure out what those are here. So for carbon, we have 7.341 moles carbon, and then for hydrogen we have 11.7 moles hydrogen. Alright, so there's the first step, convert it to moles. Our second step, we need to come up with the ratio of the moles. So we'll just set up our ratio here. We have 7.341 moles of carbon to 11.7 moles of hydrogen. And I'm going to divide that ratio by the smallest number, so 7.341. So obviously anything divided by itself is going to be 1, so that's 1 mole of carbon. And then let's see what we get for the hydrogen. We have 11.7 divided by 7.341. Alright, so here's probably the most confusing part about this whole thing. So you can see the ratio is 1.593, etc. That's obviously not a whole number. It's not really close to a whole number either. That's pretty close to 1.6 though. Okay, it's pretty close to 1.6. So I'm just going to write 1.6 there. Now you might be thinking, well, should I just round it to 1 decimal place then? Well, not exactly. The key is to actually think of it in terms of a fraction. Okay, I think most students prefer to think of it as a fraction. If you think about the number 0.6, 6 out of 10, that's 6/10 or 3/5. So this would be the same thing if I wrote this 1 mole of carbon to 1 3/5 moles of hydrogen. Okay, 3 divided by 5 is 0.6, so this would be the same thing. This is obviously not a whole number ratio. Okay, so this is where I do need to do that if necessary step. If you don't remember it, I'll flip back here and you can take a look at it. This is step 3. It says, if necessary, multiply the ratio to obtain whole numbers. So I need to multiply this whole ratio, not just one of the numbers. I have to multiply the whole thing by some number that will make them whole numbers. Well, the reason why fractions work so well, and the reason why I turn this into a 3/5 here, is because I know if I multiply by the denominator of a fraction, it'll make it a whole number. Okay, so the denominator of the fraction here is 5, so I'm just going to multiply this entire ratio by 5. So 1 mole of carbon times 5, that is 5 moles of carbon. 1 3/5 times 5, that would be 8. Okay, 8 moles of hydrogen. If you're not sure on that, you can just check that on your calculator. It's actually, 3/5 times 5, that would be 3, and then 3 plus 5 would be 8, so that's how we'd get that. So here is our ratio. Okay, 3 moles of carbon to 8 moles of hydrogen. So this gives us C3H8 for our, not C3, C5. I'm sorry, C5H8 for our empirical formula. Okay, so that is the empirical formula. Okay. Alright, the molecular formula, again, what I need to do is I need to take the molar mass that's given to us. There's the molar mass. So that, remember, that is the mass of the molecular formula is actually what that is. And I'm going to divide by the empirical mass. So figure the empirical mass. So we have 5 moles of carbon, so 5 times 12.01 plus 8 times 1.01, 68.13. Well, you'll notice that those are really close to each other. Okay, so we're going to get 1 when we do that. Now, it won't be exactly 1. In fact, let's just go ahead and see what what we would actually get. Okay, 0.999706. So like we talked about before, it's going to be really, really close to a whole number. Okay, and that is in fact what we get here. So the ratio is 1. So what that tells us then is the molecular formula is the same as the empirical formula. So here's a case where we have the same ratio, or the ratio is such that it doesn't get any simpler for the empirical formula. So here's the case where they are the same. Alright, what's left here are just a couple of practice problems, so it'll be a good time to pause the video, try them out yourself, and then see how you did. Alright, we're asked to write the empirical formula for each compound. We're given the molecular formula. We have C3H8. Well, 3 and 8, they're not divisible by the same number that would still make them whole numbers. So the empirical formula for that is still C3H8. For C10H22, I can divide them both by 2. So if I divide them both by 2, that would give me C5H11 for the empirical formula. And then finally, I just realized this is the example I made up there earlier. The molecular formula, C6H12O6, as we discussed earlier, we can divide both of those, or all of those, by 6. So 6 divided by 6 is 1, and 12 divided by 6 is 2. That gives us CH2O. So there are the empirical formulas. Alright, the last examples, actually these two go together here. Number 2 gives us the percent composition of naphthalene. We're told that naphthalene is 93.7% carbon and the rest is hydrogen. We're asked to determine the empirical formula of naphthalene. So our first step is to convert our percents into moles. So that's 93.70 grams of carbon. And again, just using the molar mass to convert to moles. Grams cancel. Let's see, that gives us 7.801 moles of carbon. And then the rest is hydrogen. So again, we know they have to add to 100, so subtract from 100. So 100 minus 93.7 gives us 6.3. As far as sig figs are concerned, you should have a second decimal place there because that percentage goes to a second decimal place. Okay, and I will go ahead and convert that to moles. Again, just using the molar mass. So we have 6.3 divided by 1.01. This gives us 6.24 moles of hydrogen. Alright, so here's the first step. Our second step is to get our mole ratio. So I'm just going to set up the ratio. We have 7.801 moles of carbon to 6.24 moles of hydrogen. I'm going to divide them both by the smallest number. So divide them both by 6.24. Obviously that'll give us 1 mole of hydrogen. Because anything divided by itself is 1. Let's see what we get for the carbon. Yeah, that's 1.25. Okay, so here's another example where we want to think in terms of a fraction. At least a lot of you probably prefer it that way. 0.25, that's 1/4. That's 1 1/4 moles of carbon. Okay, so obviously not a whole number. Okay, so what am I going to do? I'm going to multiply this whole ratio by some number to make them whole numbers. Well, at 1/4, the denominator is 4. So if I multiply this whole ratio by 4, that would give me 5 moles of carbon to 4 moles of hydrogen. Okay, because 1 1/4 times 4 would be 5. So my empirical formula, we're done with that part, is C5H4. Okay, there is my empirical formula. Alright, actually for that problem, that's all we were asked to do. The next problem goes along with this one. It gives us the molar mass of naphthalene. We're told it's 128.18, and we're asked to find its molecular formula. So remember, we're just going to take the molar mass, and that would always have to be given to you. That's not something that you could calculate if you don't already know its molecular formula. And we're going to divide by the empirical mass. So if I just calculate the mass of the empirical formula, so 5 times 12.01 plus 4 times 1.01, that's 64.09 grams per mole, that ends up coming down here. Okay, and I will divide by that so I can get a ratio. And that's going to be exactly 2. And back with those numbers, that's exactly what your calculator will tell you. That gives you 2. So what that tells us then is the molecular formula is 2 times as big as the empirical formula. There's twice as many atoms. So the molecular formula for naphthalene is C10H8. Okay, you can see just multiplying both of those numbers by 2.